So, in the last lecture we have learned the partially ordered set, and today we will see the some properties of partially ordered set or poset we call. So, and we will see that how it forms a algebraic structure which is very important in practical applications like the information flow or in Boolean algebra called lattices. So, before we introduce lattice, first we see the properties of posets, the partially ordered set. Before this, we introduce a notation normally we used for posets. So, if we remember that when we have learned the posets, the partially ordered set, we have seen that normally the relation with the operation, a relation R with operation less than equal to, or the if we consider set inclusion, the subset or the divisibility, with these operations they form a poset. R is a poset. Okay. So, I can write that this is a poset. Now, this is different operations. Now, if we use a notation like this, it is not always, it represents that it is less than equal to, but we define that R with this notation is a symbol. This is a symbol that we can use when we discuss the ordering relation in an arbitrary poset. Now, that means this relation, this can be less than equal to, or this can be set inclusion, or this can be divisibility, or any other operation. This does not, why we have used the similar type of notation that less than equal to. So, if we write this thing, that we use this notation which is similar to less than equal to, because that normally the posets are very easy to understand with the operation less than or the relation, that means that ordered set, and that is why it is a similar type of thing. So, now onwards we will be using this notation to represent an arbitrary posets, and we will also use the term less than equal to, but we remember, we must note that this is not always less than equal to, this can be any other operation also regarding one arbitrary poset. Okay. So, that means if I write A B, that means we will be telling that in a relation, in a poset R, we will be using the term that A less than B in relation or in the poset R this. Okay. Now, we see some of the properties of poset. So, this is a convention that we will be using. Now, first we see some greatest and least element of a poset. So, we define greatest and least element of a poset. Now, sometimes if we define that sometimes there is an element in a poset that is greater than every other element of the set. So, such an element is called the greatest element of a poset. Now, we must note that sometimes we get sometimes, not always it exists. We must note this term. So, we can write that this element is unique and this is called the greatest element. So, I can write that greatest element is unique if it exists. If it exists. So, if we call that A is the greatest element, if A is the greatest element in the poset S, then I can write for all elements B belongs to S that B is less than A, because just now we have defined the notation this as if we always tell this is less than, as we have defined or we have introduced this notation. So, this is my greatest element. Now, similar way I can define my least element. So, for my least element, that again sometimes we get an element that is less than all the elements of the posets. So, we can write that if an element that is less than element of the poset is called the is the least element. So, if A is the least element in the poset S, then I can write, then for all element B belongs to S, A is less than B. And again for least element also, that least element is also unique of a poset is unique if it exists. Okay. So, it is unique. If we take some example, let us see some example that we determine whether the posets below have greatest element, have greatest or least element. Now, we know that Hasse diagram is a representation of poset, which is that minimized digraph. So, I give the Hasse diagram. So, I write a Hasse diagram like okay. I give a node A, B, C, D. So, this is my figure 1. Okay. This is my figure 1, or I give say A, B, C, D, E. This is one Hasse diagram of a poset, figure 2, or reverse of the figure 1, A, B, C, D, figure 3, I get this type of A, B, C, D, figure 4. Now, we see that for figure 1, it has some least element, it has some least element A, because A is less than all elements of BCD. So, it has a least element, okay, I write. So, figure 1 has least element A, but no greatest element. If we see the figure 2, no least element, no greatest element. Here greatest element is A, but there is no least element. So, for figure 2, for figure 2, has no least element and also no greatest element. Figure 3, just now we have seen, figure 3 has greatest element say, but no least element. We see figure 4, figure 4 has greatest element as well as least element. Here it is, here it is. So, figure 4 has greatest element A and least element D. So, this is greatest and least element, but if it exists, not always the greatest and least element exist, as we have seen for figure 2 has no least or greatest element. Now, we can define the some greater some lower bound and upper bound. That means, sometimes, so we can tell the upper bound, we can define the upper bound and lower bound. Since we have just now we have seen the not always the greatest element or the least element exist. So, sometimes it is possible we can define like that. Again here sometimes we remember, sometimes it is possible to find elements that is greater than or equal to all the elements in a subset A of a poset S. Of a poset S. Now, if and this element is called the upper bound, greater than all the elements, and this is this element which is the upper bound of A. So, if an element u, say u belongs to S, then A is less than U for all A belongs to A, because we consider A is the subset of the poset, and we see that A is less than equal to U for all U belongs to S, then U is called the upper bound. And we will see upper bound is not unique. Another is upper bound is not unique. There may be more than one element in the poset S where this property holds. Similarly, we can define the lower bound. Similarly, for lower bound, we can write for lower bound, we can write an element L belongs to S, L is less than A for all A belongs to A, the subset A, capital A. Then L is called the lower bound of A. And again lower bound is not unique, lower bound is not unique. So, we get some upper bound of a subset A, we get some lower bound of a subset A. We take some examples so that it will be clear how to get the upper bound and lower bound from the Hasse diagram of a poset. So, we take an example. Okay. So, for a poset, we draw some Hasse diagram. Okay. We draw give some node name. So, this is A, B, C, D, E, F, G, H, I. We connect, this is also some diagram is there. Okay. Now, we consider the so this is one poset, okay, relation S, and this is the Hasse diagram of this Hasse diagram of the poset this. Now, consider the subset A, we consider different subsets A. Say for the first case, I consider A equal to some, okay, we consider ABC, and we see that what will be the upper bound? So, upper bound we call UB is E G H I and lower bound LB is A. Similarly, if I consider the subset as HI, then we see that there is no upper bound because H and I, so there is no upper bound. That means we do not get any such element in the subset A which satisfies the property, but there is lower bound, that in this case that lower bound is since it is HI, so lower bounds are A, B, C, D, E, G. So, all will be the lower bounds. So, lower bounds are lower bound A, B, C, D, E and G, all are lower bound. Now, we define the least upper bound. LUB, that X is called the least upper bound of A if X is an upper bound that less than every other upper bound of A. Since just now we have seen that there can be more than one elements in the upper bound. So, now we are finding what is the least element with respect to that poset, that S less than, then that can be defined as the least upper bound. So, it is one element, only one element. So, LUB is, I can write, so that is less than every other bound of A. So, I can write that LUB is only one element, that means if it exists, only one element if it exists, because we have seen that even upper bound may not exist, then least upper bound obviously will not exist, and in notation we can write A is less than X when A belongs to A and X belongs to, or X is less than Z where Z is upper bound of A. Z is upper bound of A. Similarly, we can define the greatest lower bound, we call normally GLB of A, and notation by notation. So, x is the greatest lower bound of A if x is a lower bound, that is greater among, or I can write all other greater bounds are, I can write such that all other lower bound are less than A, less than x. And I can write in this way simply that y is GLB, greatest lower bound, if Z less than y and Z is lower bound of A. Now, with these properties we can define lattice as the, now we can define the lattices that a partial order set in which every pair or every pair of elements has both least upper bound we called LUB and greatest lower bound called GLB is called a lattice. And lattice is a very important, it is an algebraic structure and which has application both in, as it has application in information flow, in communication or in Boolean algebra. So, if I draw a Hasse diagram, some examples if we see some examples, we draw some Hasse diagram. See, it has just now we have seen that it has both A as LUB, D is, so it is a lattice. It is a lattice. If I consider I give, it is not a lattice, since if I consider BC or DE, for DE it has GLB is A, but no LUB. So, it is not a lattice, but it is a lattice. So, if we consider that earlier we have considered some power set, if we remember the examples of power set of S ABC, then it has some least upper bound, and which is actually, if I consider 2 nodes, if I consider the power sets. So, LUB is the A union B, and the GLB is the A intersection B, where A and B are the nodes of the PS power set or the poset, because we have seen that it is a poset. And if we remember, the nodes are that empty set, then A, then B, C, AB, AC, BC and ABC. So, always this exists, the A, B and A union B, that means GLB and LUB always exists. So, it forms a lattice. So, some other examples that we have seen, that say divisibility, if we consider examples of some set S and say 3, 6, 9 is the set and the relation is the divisibility, or the relation we can see is the divisibility. This is a poset, say, and then we can see that LUB, the least upper bound is nothing but the LCM of 369. That means which is a multiple of 369 and is 36. So, it exists, and greatest lower bound is, in this case, 1 and 3 divides all the elements, divides 369. So, lower bounds are 1 and 3. So, greatest lower bound GLB is 3. So, both LUB and GLB exists, and it forms a lattice. So, it forms a So, we see that earlier the examples we have seen that posets, and that some of the posets with some operations, like here we have seen the division or the power set, they forms the lattice, and lattice is a very important algebraic structure that has uses in information flow in communication and the Boolean algebra, etc. So, with this we finish this lecture of the posets and this property and that how it forms a algebraic structure like lattice.